Good, okay. Hello everyone. My name is Xiyang Chen, and I'll be leading the discussion of this talk. I work for Rango, a web consultancy. We recently started a machine learning practice as well. So this paper is going to be about mostly about attention. So its name is the attention in the name is this is what we call jointly learning to align and translate. That's I think the entire paper mentioned attention like once, but as I was digging deeper into the paper, I realized that this is not quite the original attention paper. I was trying to find who originally created attention, and then I realized that it's I just couldn't find the original attention paper because there are many precursors that was in the image field or even in the CV field that has like similar concepts. So it's really hard to attribute like exactly who invented it. But I think it's safe to say that this is, I'm trying to say that as narrow as possible. This is the first paper that applies attention to neural machine translation, or probably in NLP. Yeah. In general as well.
Yeah. This gets the most citation with regard when people talk about attention. That's what they're referring to. Okay. Mostly in NLP.
Yeah. Okay, yeah. Okay, so that's why I thought the other metric is basically it has a very high number of citations. So that has like a big impact. How many of you have seen this paper before? You have. Oh, you have. Okay, so I'll be probably leading the discussion. So if some of you who are who has any point, feel free to chime in for a person a little more knowledgeable than I am. So let me test the clicker. Is the clicker working? It's supposed to work. It is not. Okay. So the little outline of our session. First, we're going to talk briefly, give a formal definition of what is the task at hand. In other words, what's the formal definition of a translation task? In this case, we're translating from English to French, I think. And next, I'm going to introduce briefly on baseline. On the TLDS Classics paper list, there's also the sequence to sequence paper. So hopefully, like in the future, we're going to expand on that at some point. But just for the sake of understanding attention, I'm going to go briefly about the just give you a refresh. Many of you probably have seen this on the basic encoder-decoder model. And the third part is attention, which is basically the main focus of the topic. And then we're also going to be talking about like bi-directional RNN. I am not sure if it's the first. Okay. They are not the first one to use it, but this is just an attempt of basically combining a lot of the techniques to basically improve the score. So we're going to touch briefly on that, and finally experimental results, and at the end I will raise probably 3 points for us to discuss. If we have any other comments, feel free to comment. So okay, definition of a task. We want to translate. Essentially, you want to translate from one language to another. That's essentially what it is. And we have input X, a source language, and target language. They are source input for each instance has a variable length, and the target sentence may or may not have the same length, so they're different. Our vocabulary of KX and KY are vocabulary size, so the vocabulary size could also be different. Oh, okay. Oh, yeah. Of course they're different, but they're different languages. So yeah. So ultimately, this is the goal. Kind of the goal. Like we want to maximize the probability of the target language sentence conditioned on the source language sentence. And this is basically a simple example. So what you can probably notice here is like in different languages, word order is different. so that they come in at a later time. So in order to create this, like before the, I think this paper came out in around 2015, around that time. I think the neural-based method also started recently. So a quite successful one is basically this encoder-decoder encoder-decoder model, which was created by, I think the paper was published by Google, people at Google. So have you all seen this? You have all seen this, right? Okay. So these two pictures they're the same thing. Like one is a very simplified version. The basic idea is we have an encoder that takes the input sentence and pass it through through a bunch of hidden layers and produce a fixed length vector. And we use this vector as a conditional and feed that into the decoder. And maybe as we progress, we use the character or the word, depending on which level we work at, and along with this conditional encoder, and we sort of progress it and created a new state and propagate it through. So that's the kind of the RNN model.
So are you okay? I'm not familiar with this. Are you tokenizing the initial sentence and you get one vector per token?
Correct.
So it's not a sequence model, right?
It is.
Oh, it is a sequence.
It's a sequence model.
Okay.
This becomes this is a representation of the entire sentence.
Of the sequence.
Yeah, not the token.
All right.
Not the token. So this is another more detailed diagram. Just basically look for materials everywhere. The good thing about the classic papers is like there are many interpretations online. There's still slides everywhere. So this is the same interpretation and hidden state. We're going to go into details a little later. And here we have an encoder. So I want to notice two things. One is obviously this is fixed length. So this is fixed length architecture. The other thing is, I'm going to say like everything. This encapsulates the entire sentence. So this is, in a way, I don't know a good word like dense or most of the burden falls in here, in terms of interpreting representing what the sentence is. So, okay, let's move on. So this is the definition of the encoder. X is the input, again, and H represents the hidden state of RNN. I think in this paper, they're only using one layer, like there's no stack RNN, so it's hidden state of HT. T means so this is unrolled like through time. And T is basically the hidden state at time T. F is a nonlinear function. So essentially, we're gonna, because the details of the implementation is not the focus of this talk, but I think I have a few slides that actually details what they're using with F. I think they are using a RNN called a grRNN, which is like the gated version. In the paper, they also said LST and PM could probably just work as well. And once we got the hidden input, hidden state at each step, we're going to be able to calculate the C. C is basically, this is the broadest formulation. C is basically a function. Again, it can be linear or nonlinear. Q can be linear or linear. C is a function over all the historical states. But in a lot of the sequence of 6 implementation, like Q is simply basically the H from the last step. So this is like another layer of formulation from the paper.
Where is this concept of time here? I mean, the sentence has been tokenized.
Sentence needs to be tokenized first, yes. Or you can also work at a character level.
So what is the time what does time mean here?
Okay. Good question. Okay, time here is so in here when you see all the RNN, they're kind of like the same thing, like in terms of weights, but they're unrolled over time. So it's basically a way of representing the
Okay, so
sequence.
the
So
time
the way
series,
we
but each word comes in one by one.
Correct.
yes. So in order
Start with the time.
to train this is a good point to raise because later which related to Joe's here. What you observe is that you have to do this sequentially.
Yes.
There's no way of parallelizing this.
Yes.
So you have to do it like basically inside of for loop, like in terms of implementation.
So this first picture you showed where all the weights were there, that's kind of a like a coarse grained representation because all these weights like on that previous one,
This one?
that all these weights have been obtained actually through a sequential way. This one stack of weights have been obtained through a sequential way by putting one word at a time in the
Yes.
encoder.
Yeah. So it's sort of like it works this way. It's oh, this one?
Yeah.
Oh, this is how should I? Okay, this is decoder is here, which is basically the internal representation is here. This is unrolled over time,
Yeah.
right?
Okay.
Is that?
But I think he's asking whether the fixed length vector that you get at the end of the encoding process, that is what you are explaining in the next slide, right? It's after it's gone through the entire RNA.
After after you have gone through the entire history,
Yes.
and here you have an option. You can choose to actually at the end you get the final result of the representation, right? So a lot of the sequence based model they just take that. So that's why like Q, like which is basically this is essentially the last step.
Yes.
Or you can devise like probably more complicated formulation by incorporating results from previous steps. Is that clear?
Yeah.
Okay.
So Q is essentially the function that all the blue boxes are applying.
No.
No.
Q is the blue box is F,
Oh, okay.
and Q is okay. So I was hesitant if I should introduce this layer because if there's no Q, you say C equals to HT. That'd be a lot clearer. So basically, the final encoder, this thing we get, is after you calculate, propagate like everything through time, like we kept forward from a calculation through time. Eventually, you get the final HT. And in a lot of like practical cases, they just use that as the final representation of the sentence.
But are there other representations that you can use?
Yes.
Are there other?
So mostly nowadays uses context vector, is that hence C, and the context vector is a combination of the last HT, the last hidden layer, and some other hidden layers. But this is a classic paper, so let's just stick with it. So that the last hidden state is theoretically the most important one because it gets to pick what diminishes in time and what doesn't. So the information that's theoretically it's keeping in the last hidden layer is what you want.
Yes, because it had gone through everything, all the inputs in here.
It has a choice to get rid of, to remember or not.
Yeah, remember, yes. And okay, we're gonna touch on that point like later, very soon, in 2 or 3 slides. So once we got a encode like a representation, then we feed this representation into the decoder. So decoder is also so the input of the decoder is basically what you get from the encoder, and it's got fed into it, fed into the decoder, and again you do basically this forward calculation through time. Eventually, you will arrive as you go through time. Every time it will basically output one token at a time. So again, this is a very broad formulation. There's no details. We'll have slides that tells you exactly what G is. So G basically takes the previous input and the current state and basically the condition of the encoder C. So the thing you get from the encoder, the representation from C. So that's basically the general formulation. So that, any questions so far?
So I'm still confused about C. So is C something that you're learning?
C is something after you have, for a particular example, you input every single token through time. Eventually, you will arrive at a representation that is C. C is something you get passed from here to here.
C is the same as H capital T in this case.
Yes, again, C could be just H capital T.
So what's the C1, C2?
C1, C2.
Right, exactly. Yeah.
Where's C1, C2?
Under green boxes.
Oh! Okay, I apologize. So this is probably, I'm using, I didn't notice that because I copied someone. This is actually the attention part. So I'm going to get to the next step. But sorry, this I probably should have used this because it's this has attention already. So the next thing, like as soon as you got his attention, you will no longer see 1C, or you will see C1, C2, C3. Yeah, sorry, I probably should have erased this.
So what was that, Steve? Was it your sequence? What's S? S?
S?
In your G?
Oh yeah.
States on the top.
States? Okay.
This. I knew we'd be confused at the time, so I inserted this line. So one thing that I was really struggling. I was looking with Jake. We were really struggling about this is the basically notation of this paper. So I guess this is probably helps to clarify before we move on. We have hidden state in encoder, hidden state in decoder, and for each time step we have an index. Here in encoder and also in decoder. So in the paper and in subsequent slides, here is what the original paper was using in order to kind of distinguish where things are. H, whenever you see H, it refers to encoder. Whenever you see S, it refers to the decoder. But structurally, they're the same thing. But it's just like they exist in different places. Some later paper uses H bar to represent H. H, but in here, honestly I don't know what S stands for.
Probably hidden state, and then H is hidden.
H.
H is hidden, S is straight.
Okay, that explains it.
So,
And
is for every RNN in the encoder, is the previous hidden state also an input to the next RNN state?
Yes.
Okay.
Yes. So in here.
Yeah, and so H0 is what, some prior?
H0 usually I see in actual implementation just set it to 0.
Okay.
Yeah.
Okay. And the other question is that in some languages, as you can say, like can be like words which go back and forth, but in principle, you have the length of H0 vector is the same as the length of X vector, at least at the encoder level.
The same length.
So if you have 5 words, you have 5 hidden.
Correct.
Right, to begin with. Then it can change as we move up the layer.
Yeah, so when you're encoding, at each time step you're producing a hidden state.
Yes.
And you can keep that. And
Yes.
more often than not you actually keep that.
Yeah.
Usually the number of the steps are smaller than the size of the sentence, because let's say your sentence is 100 words, but usually you keep the time step as small as something wrong.
Yes, we'll get to that later. So I think what you're saying is that if you're encoding a document of 200 words, your last hidden state, which is like 20 dimensions, can sort of capture the entire. That's correct, and that's theoretically the first way people thought about it. But the more we improve the performance, we realize that we need more of that context, so we keep a lot of those states, and we use attention. So we'll
yes. That's a very good point. It's actually one part of the reason why attention is needed. I'll talk about the drawback of this. So very soon. So J is based. So go back to this. J. Whenever you see J, is for the H, which is for the input or the encoder. And I, you will see later, is for the decoder. So the way you can sort of internalize this is basically for any things I'm trying to produce, I need this. I probably need to look at the J's from the encoder. So which will become clear. So for now, just say when you see J encoder, I decoder. So it will become clear soon. This is the same thing. Input, just basically to recap, we got input a sequence, encodes it into a fixed size representation, and put it through the decoder, and it sequential every time outputs a token. okay, this is a repeat of the same thing. So, so empirical results, this is a previous paper. This is the Google papers, Suskewer, 2014. And here is just give you intuition on what that C. Like if you do a dimensionality reduction, such as PCA, because the encoder encodes the entire sentence, so you can see spatially that sentences of the same meaning, like actually they tend to be close to each other.
In the embedding space.
Right. So it was about so you grab the embedding space vector for each of them with PCA and then.
Correct. I think that's what it did. Yeah. So the paper basically, I forgot. Like one paper said, like this is better than bag of words, just because the word order matters.
Which one's the bag of words results?
There's no comparison. It just this is like you can't. Maybe if you do it with bag of words, then maybe this is like because they are probably okay. John admires Mary. Mary admires John. Bag of words would be exactly the same thing.
Right. Or even word to word.
Yeah,
Any
you
non-RNN wouldn't be able to
That's
do
right.
the sequence.
Doesn't consider the order.
Yes. Okay. So now comes to the problem of RN. First of all, the burden, I mentioned the burden of C is intuitively you can see this tries to encapsulate a lot of things in once. The problem with that is that it doesn't say on this slide, but I think if you do RNN, in theory, if you do pure RNN, RNN has this, just by RNN with no gates and just pure RNN, it has this tendency to memorize, to put more emphasis on things it has seen recently. Because intuitively it makes sense, because this probably for one way or another, like it only cares about the more recent stuff. If you have a very long sentence, then the previous content is forgotten. People have created gated, or various gated, like LSTM, GRU. In here, they have, I think, they have their own gated version of RNN. So basically, it's you selectively let information pass through. I think that's the good comparison. The end result is it somewhat alleviates the problem, but not completely. We can expand this. I think I have my own, I guess, explanation. This based on nothing but like this intuitive explanation. We can talk about this in the discussion, which is a point I'm going to raise. But bottom line is, it's not good enough. Even if you skate it, it's not good enough. As you can see, RN encoder. I'm not sure if they're using gated. Oh yeah, this one they're already using like gated version of RN, some gated version. But still, as the length of the sentence increases, performance drops.
So what's the BLU score?
Okay. I knew someone would ask this, so I have a
Cheat sheet.
cheat sheet. Can you help me with this? It's okay. Yeah, go ahead.
I mean, I will try to remember while I start talking about it. I worked in machine translation like 6 years ago, but basically it's a measure of capturing if the inputs, like how much the input sequence and the output sequence as two different languages match. Some sort of a more fancy edit distance. You can think of.
Okay. So okay, I took a very sneak peek at a paper before I came here because I kind of feel like somebody's going to ask this, but actually, yeah, it's basically the problem is essentially you ideally want humans, good translators like professionals, to evaluate the quality, but that's prohibitively expensive and could take months. But what you do is like you try to come up with a metric that's close to like human performance as possible, and they incorporate a whole bunch of things. Like the basic thing is word counts as precision, but if you use different bigram, then they have this concept of masking, which is basically if you translate this word once, you shouldn't translate it again. So there's also this count on the maximum occurrences, and that's also taking the formulation. And they use a combination of 1 gram, 2 gram, 3 grams, 4 grams. I think that's the blue score. And the end result is if some phrases that machine translated end up being similar, very similar in the sense that this program exists also in some of the human reference translations, then you score, you get points. So it's a combination of all those like factors. Is that good? Yeah. So which end up kind of in a way simulate a human judge, but it's definitely not good as good, but it's good enough for you to do metric evaluation very rapidly.
Yeah,
Okay.
so the difference from edit distance, in edit distance you look at characters, here your atomic units are words. And yeah, bigrams matter because you want things to occur in a certain order, and it changes the meaning if they're swapped.
Okay. And so the final point is, if you look at intuitively how humans do translation, and they probably do it differently. If you want to translate from English to French, I think the English and French, there's still a language that's very similar to each other. So if you look at word by word, that's fine. But if you think of language like Japanese, which is like the order of subject and verb, object and verb could totally change. So a human translator essentially keeps looking at a sentence, remembering what it has have seen, but the humans are also allowed to look back. Like maybe there's something it hasn't translated, it allows to look back at the source and see and maybe translate later. So that's kind of the intuition behind it. Okay. So which leads to the Bagnall paper, the paper we're going to be presenting today. The main contribution could be summarized, I suppose from somewhere else, could be summarized as follows. I think the most important thing is the third point, because later papers actually prove that maybe if you already have attention by direction, RNN may not help as much. So there's a follow-up paper like in the following year that basically said that we use the unidirectional LSTM and we achieve similar, if not better, results. So I guess the main part we're going to be focusing on is basically attention. So attention is, okay, I'm going to go into this in detail. It's basically on a very high level, a weighted sum of the hidden states from the input, in other words, from the encoder. So that's essentially what the attention is. All right. So this is what they call attention, learning to align and translate. Back then, the term attention was probably not as ubiquitous. So again, in the basic sequence-to-sequence encoder-decoder structure, encodes a whole sentence into a single fixed length vector. However, if you do it with an encoder and decoder with attention, here's the distinction. It encodes the input sequence. First, the length of your vector, your representation could vary. That's the first point. The second point is, while decoding the translation, you are selective, essentially. So that's where attention comes from. Like at every time step, you have the option of focusing on different things. So it's like a high level intuition. So then that leads to the definition of this is the decoder part of the attention. We're skipping encoder because encoder is essentially the same with what we've seen. So the decoder is the part where it actually starts to care about, okay, what have I seen? The formulation is essentially this. So we want to calculate the probability of the current time step given the history, like a list of history of tokens, plus the input, the source translation, and the broadest, the highest level of formulation is basically a nonlinear function over the token you have seen at previous step plus this SI, which is basically the hidden state of the decoder plus CI. CI is basically which we'll see later. Notice that C now has an index. Like it's not before like C is the fix for the entire sentence. But each time step, we will have a different C. So that's the difference. Yes.
So for the conditional probability of yi, why on this side we have for the nonlinear function we have only yi minus 1? Like what's the relation that the previous translated word only is important and not the history? Because on the conditional probability you have y1 to yi minus 1, all of them, but on the nonlinear function g you only need yi minus 1.
Good question. Yeah. I think the assumption is that a lot of those things will be kind of folded and encapsulated in here.
So I think the hidden state and the context, I think the way they're modeling it,
they have taken into account
the
taken
hidden
into
state
account, yes,
and the context is capturing all the other information.
Okay.
Yes.
I think this is the model.
Yes, and here's the part where it's starting to get slightly complicated. So, but hopefully I broke it down. Hopefully we can go through this like in various ways and until kind of understand. So in here, the calculation of the decoder state becomes a little different. So it becomes slightly complicated. So remember before that it's essentially dependent on the C and on the previous hidden state and previous input. But now it's slightly complicated. It's dependent on the CI. So this CI will actually be the we'll have a few slides dedicated to CI, how to calculate the CI. Notice that the context vector varies. Okay, I covered that. Probability is conditioned on a distinct context. Was I talking about the same thing? Okay.
So in the truest sense, G is actually a function of yi minus 1, si minus 1, and ci.
G, sorry, which one? Y minus 1, si?
Minus 1 and ci, because si is essentially a function of these things, right?
Okay, this is the final output. So this is what you're producing here.
Yeah.
But this is how you calculate
SI.
this SI.
Yeah. Okay. Yeah.
And again in this, I guess in this paper we don't talk exactly. I have a slide in the end, like that tells you exactly how to talk about this. But they essentially they want to focus on this part, so they shovel this all the way down to the last page of the appendix. So indicating it's not very important, I guess. And it's pretty complicated actually, but we have to go through this if we find time. But the focus is probably on this, how you calculate the hidden state in here.
So naively, can I ask another question? Naively, I would have thought SI is just a function of all the I minus 1 stuff. So why does the hidden state depend on the context at time I and not at I minus 1?
Because it's not all about I minus 1. That's
wait.
Hitler's going to talk about it.
Why does the context depend on I, not minus 1?
Why does the hidden state depend on the context? So that's, I mean, I guess it makes sense. But if you were just, it depends on the context at time I and not the previous, like not what you've previously seen, but
it does.
Well, that's captured in Y.
That I'm sure that's captured.
Actually,
but CI comes from the encoder stage, right? So you don't need to wait to see CIs, like you know all the CIs.
Oh really?
But Y and S you have to generate as you go.
Actually, that's.
No,
it's more complicated than that. I think CI also depends on S, I minus 1 something.
No, that
I
is.
forgot.
You're right. Yes, you can. You can use S to compute C, but most of C, if not all, is computed in. So it's usually the case that encoding takes place for the entire for all the tokens you have in your input, and then you go start decoding. And at the decoding steps, you may take different Cs. Right, but mostly C is the hidden states in your encoding time. A little bit of it comes from now what have I seen before? It may or may not. We'll see.
Okay, we'll see. Honestly, my mind's not blank right now, so let's see. Okay, so this is okay. I don't want to confuse you, so I'm not going to linger on this for too long. This is just give you a concrete example of how you compute SI. It's basically this: a whole bunch of gates, update gates, reset gates, which is SI is this is a linear interpretation based on the update gates of Si minus 1 and S tilde, and S tilde head is this is basically the gated recurrent model. I think they call it GRRNN. but I don't, because this is not a focus of this paper, this is just basically one formulation.
Yeah, but if you have questions, we can talk about it.
What if you have questions?
But if people have questions, like it's
Okay,
basically just
I have a question. Esan, can you explain this?
we can go back to this because I want to focus on
let's,
attention.
okay, let's go back to it.
Okay,
Go back to it.
but again-
but high level, there are 2 gates in a GRU. Basically,
So this is GRU?
Is it GRU?
It is GRU.
Oh,
Alright.
we're just not calling GRU.
So you have 2 gates, right? You have update gates and a reset gate, right?
Oh yeah,
It's just the CI is
LS
a
I didn't really, okay.
LSTM has 3 gates: input, and then
Forget.
forget, and an output gate.
Okay.
But basically, it tells you
I got my answer. So
You
this is
did?
GRU.
it is GRU.
Okay.
Yes.
Okay. Sorry. And remember the CI. So here's how you calculate the CI. CI is also known as expected annotation because it is ultimately derived from a annotation. What is annotation? I'm going to tell you. So it's probably good to. I was hesitant to if I should go this way or should go backward because it's probably not. There's no perfect way. So annotation is an expected annotation because it's going to essentially be a weighted sum over things you get from the input from the encoder state, and probably many people can recognize it as a softmax. It's a softmax over something, and what is something? This something is Eij. That's why I was having a slide I and J. Does anybody still remember what I and J stands for?
Yeah. So I is the decoding step, and J is your encoding step.
Very good. Okay.
I want to draw the attention to CI though, because we talked about it earlier. So C, it's all about the H,
Yes.
C is all about
which is your encoder.
Yes.
Right? C is all about encoder. Just
And
like that.
Says
the
all.
context is there is nothing sequential about it. You know the context. Once encoding has been done, you know the context values
Correct.
essentially.
Yes.
Right?
Well, you know, so C it has an I, right?
Yeah.
So okay, so no. So at each decoding step,
Yes.
you have a different context.
Yes.
Does that make sense?
But that's kind of related to each xi.
X.
So every token
correct.
has its own context.
Well,
Essentially.
if it's talking about this, then it's XJ.
There are XJ and YIs.
Yes.
Right?
XJ,
So
Y, right.
Sorry, yeah, xj, sorry.
Yeah. So so XJs are your inputs. At decoding step, you don't really care about inputs anymore. Directly, at least, you have access to the hidden states.
Yes.
Right. So now we're talking only about the hidden states.
But in terms of length of vectors, xj vector length is the same as the context length because so if you have 10 tokens, you have 10
correct.
hidden values and you have 10 contexts.
Correct.
That's it.
Yeah,
And then
usually-
you're moving up the network.
Yes.
Yeah.
Usually, when you can make them different, but usually when I write RNNs, my context, hidden states, and S's are usually the same length.
Yes.
They don't have to be, but like C has to be. 'cause
Eventually, that's the part I am a little confused. That eventually, in a language, you might need less words to say something
Yes.
in the French language than in English.
Yes,
So how
yes,
is
yes.
that going to happen?
Yes,
I'm
I think
looking
we'll
for that.
Yeah, I think we'll address it. If not, we can talk about.
Oh, okay, we're gonna go back to that. Hopefully.
Yeah.
Okay. So this is sort of like circular definition to Amir's question earlier. Eij also depends on C S I minus 1. So I realized what's probably missing is probably I should give you like a high level overview of what's going on. So you essentially, I guess the intuition is for each time step you construct the CI indicating your attention. And the way you construct the CI is basically you get a weighted sum of all the hidden states from the encoder. Actually all the way up to H1. So this model, this paper is using the entire history. And for H of the J in here, Hj, we're calculating a weight alpha. And this is basically how you calculate alpha. I tend to basically just get rid of this softmax layer because so getting away, I just look straight at Eij. This is just a normalized version of this. So this is called a alignment model, or in other words, it's called a score. It's a score on how well precision I of output, how well a particular precision I here is, which is basically our current thing we want, the current token we're trying to predict, and precision J of the input. So then we have basically this matrix of values, E, I, and J. I is my output token, current output token. J is token at every single step from the input. Okay, so where's we go?
So for a given Si and Hj, what does the A do? If it's
A is a nonlinear function. And okay, I thought like
is it like a dot product? Like can I think of it just as a dot product?
it can be, yes. And
Sometimes they sum.
it's good that you raised that. Remind me, the other thing I want to point out is that since we are basically, this is calculation, there are potentially a lot of things to calculate. So this is essentially T, if your input is Tx, Tx and output is the length of input, Tx, length of output is Ty, so it's Tx times Ty. It's very heavy. Not heavy, it's like there's a lot of things to calculate, so this needs to be light. So I can talk right now, but that's one of the discussion point actually. The choice of this could be as simple as dot product. What they're using is something they call a concat, or you could also do something. You do a multiplication. You do a matrix in the end, in the middle. So it's like S W H. That's another form.
Because the dimensions are not the same.
Yes, exactly. There are pros and cons. We'll get into that.
And in all that cases, they are dot products.
Yeah.
And
Like the simplest example is probably a dot product.
Yeah.
Well, and some.
Correct. If the length is the same.
They want
Yeah.
to be scalar.
EIJ is going to be a scalar, right?
EIJ is going to
Which,
scale.
which
Oh,
the
okay.
predicted with some, but
Yeah.
is weighted.
Yeah.
So what is EIJ measuring? I don't get that. That's just a similarity of the context vector at the two different steps in input and output.
You could basically say how much attention, like for a particular word, like right now you're predicting a word, like at a particular position, how much you should pay attention
Right,
to
I
each word.
understand that part. What I don't understand, or what I'm trying to clarify is the way you construct that amount of attention or that weight is by looking at how similar Xj is to Si minus 1, and then somehow normalize it.
So,
And then
so
It's not necessarily similar, Larry. Okay, go ahead.
Is this because we said dot products that you say have
Yes.
similar? So that's a parameter that we learn. It's just a hyperparameter that so that if say the A is a function, we start with the random vector, and then we learn as we go on.
either
You learn that the thing. So let's say you want to compute. You have some. It's A of x, and x is a vector. Okay, that's what it is. And then what this function does is it multiplies a v, another vector, by your x, which is your input. Okay, that v is randomly initialized, so it doesn't bear so much of a
So
semantics.
that's not present. So that's more like the transformer. That doesn't mention that there though. But that is what's happening. There are random vectors that are participating.
So are you saying are there other parameters in here,
Well, I mean, I guess you could think of them as parameters.
like the v that you're talking
Like,
about?
yeah, is there a V in this early model? Because it looks,
yes, there's v in their formulation in this paper, and yes.
So they have the keys. What they call it, key value pairs.
I have a slide for that one, so maybe you can talk about it. Sure.
But before even going to details of A, right? Because you guys are talking about the potential implementation of what A can look like, right? So before even going there, like I'm trying to understand what is the logic of, setting up the coefficients like this.
I don't know if I get. I'm just take a bash at it, but I think the reason. Wait, which coefficients are you talking? Like the ij?
Well, alpha ij is set up as exponential of E normalized, right?
Right.
Yeah.
So, and then there is a definition for E, which is some function of
So,
vectors.
so let's think about it this way then.
Okay.
So you have your S's, you have some hidden states for your decoder,
Yeah.
you have some hidden states for your encoder,
Yeah.
right? Based on them, you want to have some value. The more it is, the more aligned that word is, as opposed to your input, right? So that's just a scalar. That again, as the value goes up, the more alignment you have between the two hidden states, right? Each hidden state represents a word. One in the encoder, it's a source language, the other in the decoder. Basically what you want to do, you have, I don't know, say five words in your input, you want to generate, I don't know, 5 words in your output, you want to see how aligned they are.
Maybe, hopefully, maybe this visual could help. And this is basically, this is the alignment of the
so that score,
value.
that score tells you the alignment score, how significant the alignment of those two potential words are. And now it's a scalar, you want it to be probability, that's why you normalize it. And the normalized version of it is called attention.
What alternative were you thinking of this kind of
Yeah.
coefficient lookup table, whatever you want to call it?
Well, I don't know. I guess what I'm looking for is like what properties does that A have to have, which I guess what S1 is saying is one property of that.
Okay, let me just give it here. Since we're already here. So here is there's a follow-up paper that tested on 3 different formulas of A. These are 3. Like they use different H bar is essentially the S thing. So
The S is at the bottom.
this is what this paper is using, and then there's the other 2.
So they are using B. They are using random initialized
Yeah, they're using
vectors.
B. They're using B.
I mean, W is also random initialized vectors. But
Yeah, these are random initialized. This one doesn't. Then this one doesn't introduce any additional parameter, right? I suppose.
What is the
So it's a
B
direct similarity.
What is the B doing in addition to the W's?
Yes, that's my question as well.
So because you want it to be a scalar, right? So matrix times.
Okay, so it's like the
Yeah.
same
And-
dimensions.
And this is
Matrix times
yeah.
vector is a vector.
Okay. This is called concat.
I mean, my intuition, to be honest with you, is that, I mean, yes, you are trying to have some kind of arbitrary internal description of similarity or alignment or association. I think that's what it's sort of trying to say. And the reason why the problem I think that I also struggled with is just that the notion of similarity is designed to be trained, so it's literally arbitrary, right? The only structures that you need is you need some kind of property that's going to be, I mean, preserved in the way that a dot product or a something similar would.
Yeah. If this helps, I haven't read through the entire paper. So in here, they only use one layer. The H is basically is in the representation of the entire thing. So this also has an extra burden if you apply attention to it, and the gradient has to be properly bad to learn that, to force these two to have similarity. In this paper, the follow-up paper, this paper, someone else did, they basically, I think the way they did is that they kind of alleviate that a little bit. Number one, they have different layers. And number two, they probably, this entire hidden representation that doesn't need to be forced to be similar to the decoder. So because you have multiple hidden states, so only part of it will be responsible for that.
Is that the hierarchical attention model?
It's called hierarchical. I don't know.
No, I think that's different.
Oh, okay.
It's different.
In hierarchical attention, you compute attentions on sentences, and then
That's
also
right. Yeah.
on words. But I just want to agree with the discussion that I like the question that you asked, and I think I changed my answer now to it. That there is, if you're using the dot product, then it is a similarity, but with the v vector.
Exactly. Like essentially, the
As you
first
said.
and the second description here are similarity metrics. The first one is just dot product. The second one is the weighted dot product.
Correct.
The third one I don't really understand what it is, but I mean, I
it's-
understand what it is written, but I don't know how to interpret it.
What is W actually?
It's just you're using an arbitrary basis.
It's just the same thing. You have
I think it's
nonlinear.
exactly the same thing as before, except you have an arbitrary basis.
So in actual computation steps, this is sort of how it goes about. So basically, number one step, you compute alignment alpha, or for, okay, suppose you add time step I to compute the output I, and then you compute the context CI, then you generate a new output, which is Si minus 1, and finally compute the current Si. Oh, sorry, generate new output is basically Si minus 1 creates Yi. That makes no sense. Yeah. I stole this style somewhere.
No, it makes sense, right? No. 3 and 4 are backwards. No.
Ci produces Yi, and Yi is generated by Si minus 1 and Ci. Oh, okay.
Can you quickly go back to the equations?
I think it's not consistent with what we saw, right?
Yeah.
Y minus y. Okay, sorry, so probably there may be some discrepancy in here, because I stole from three different PowerPoints. Sorry about that.
Yeah, so some of them have those plus ones, and you didn't have.
Well, there's no
This one?
negative one. That's what's missing.
Yeah.
Sorry, what is the confusion?
So y is yi derived from Si minus 1
I think it
and
should
Ci.
I think it should be Si. I think that should be Yi minus 1.
Yeah, this one should have. This is probably a mistake. Okay.
Yeah.
All right. Then there's alternate interpretation. I inserted these 2 slides because I think it's a nice way to lead up to Joe's presentation on Monday. So this is a different, more intuitive framework or paradigm to think about this attention, and it's essentially the same thing. But in here you have 3 concepts called query, key, and vector. Oh, sorry, query, key, and value, each being a vector. So the query part is essentially what we saw at Si. The key part is the Hi, basically the hidden state from the input. And finally, value could be the same with your key, or it doesn't need to be. I think this doesn't exactly translate to the we saw probably in CS like key vector, but it's a good way of thinking about it. So basically, I am currently trying to predict this word hate. This is my query vector, and here are all the keys I can look up to, and based on all the keys, I compute a different weight for each of these keys. So basically, this is an alternative way of interpreting. I think the attention is all you need paper. I use this paradigm. If I haven't read it completely. Yeah. Okay. So just a quick introduction. So here's some intuition I kind of gathered from throughout the entire paper. We have already seen this in explanation. It's self-search in here. Each time step, it self-searches for set position. So the keyword here is soft, as opposed to hard. Hard being like 1 or 0, and soft enables it to I guess essentially not miss, to be able to find more nuances. We'll see an example soon if we speak French, because that example doesn't make sense to me. So the attention mechanism is simply a network giving network access to its internal memory, which is the hidden state of the encoder. So this is the interesting point. This is the point from the blog post. That post basically argues that attention is essentially some sort of a misnomer, because what we're doing here, we're really doing memory access, recording things and retrieving them later. So they argue that you think of attention another way. By the way, the difference between what we're doing now and with the basic sequence model, if you probably have noticed, is that we will have to, right now we have to keep the entire history of the H, as opposed to previously we can discard as we go, discard space as we go. So in other words, this could be just a memory interpreted as a memory access mechanism. And finally, this is the another interesting point. It's basically, as opposed to what we saw in sequence model, where the C in the middle bears the burden of encoding everything. Here, the responsibility of accounting for information is sort of spread into a different age. So that's another point. So finally, here's the bidirectional RNN. Yes.
Just as a quick aside, I think the attention term might actually come from vision research, where it kind of makes more sense because you don't have like a memory. You just have the whole image, and you may be paying attention to like some small piece of the image.
Oh, okay.
Right. I still hate it, to be honest with you, but it makes slightly more sense in that context. Whereas here, I agree with you.
To you.
Well, it makes slightly more sense.
No, I think if I'm not mistaken, it's the vision attention is older. I believe so.
Yes.
I mean,
it's the CD.
But it's like hard attention. It's like you would just have like a bracket that looks at only one part of the image, right? That's a hard attention.
Yes. Ignore everything else.
Just look at this.
Yeah.
Anyway.
So
I have another question.
Yes.
So instead of doing this attention mechanism, what if you just had the full series of hidden vectors, like H1, H2, all of that fed in? Like, would this perform a lot better than doing that? Like, I can see.
Okay, you have a history of vectors, but how do you extract information from that vector?
That's the question. That's what I'm not sure that. Like, I know that this is doing it in a particular way, but imagine I just had, instead of that, just concatenated H1, H2 up until HD and made like a big capital H vector and fed it in. And like,
what do you think would happen?
I think it would be worse.
Why? Because like now.
Because it still doesn't know which one is important in that, right? Like what this is doing is actually figuring out which of the words or which of the sequences that came in my input is actually relevant here. Yeah. Whereas if I just give it all of it, then it's just getting the full sentence again.
Yeah, you're also creating this huge bottleneck.
Right.
Because your hidden state is now like is big.
So you're gonna have problems if your sentences are really big right away. But as a minor spoiler, I just saw a talk by Cho, and he did do that.
Okay.
He actually had all the embeddings and was propagating them vertically in parallel. Okay. So it actually can be done. It's worse, but it can be done.
Actually, I think in memory-based networks they do that. They keep all the history and then.
Yeah. So remember the question wasn't hierarchical like processing.
Yeah.
I was just if it's just raw, if you just keep the entire thing, you just have too much information, and things can happen. We can talk about it after the talk. Yeah. But that's different. So if you have a hierarchical processing, yes, sure. If you're just distributing the processes to different nodes, and then still have weights as to what's important than the other, that you're still doing sort of a similar thing.
I think Michael raised a good point, which is basically you have variable length here. So if you concatenate everything together, if you want to multiply, I assume you want to multiply that with something else, right? But that has to be fixed length. So maybe that's the factor as well.
Correct.
But whereas in here, it gives you a lot of degree of freedom because the length doesn't really depend on it.
And the transformer paper specifically, that becomes a big piece too.
Oh, okay.
Yeah.
Cool. So
just
yes.
a quick disclaimer: there are methods to deal with there are frameworks that can deal with variable length embeddings, but again, for most of the cases, your point stands the same.
Okay.
This is
too
much.
And I just realized that I probably confused a little bit. Oh no. Okay, I was trying to delete all the bidirectional graphs before the slides. Maybe I have slipped into one or two here. But here, this is the bidirectional. And bidirectional is essentially you instead of doing the encoding once, you do it twice, one forward and one backward. And what you do next is you concatenate the two. That's essentially bidirectional embedding. So the intuition here is that, some words doesn't, likewise in terms of translation, some words doesn't only have dependency on the words you've seen before, or maybe also has dependency on the things you see in the future. And if you do that, I think the end result is it will place focus on, because remember we said like RNN also implicitly has this tendency to bias against what it has seen recently. If you do bidirectional, the end result sort of maybe will be something like it will care about the words surrounding it, maybe with the added effect. I'm not sure, because there's a lot of questions, like you probably by now you realize, okay, there's a lot of questions left unanswered. Why didn't they do more appellation studies? There's a practical reason which we'll see.
So after this forward backward pass, HI is a 2x(n) matrix. The 2x(n) vector with n is the number of tokens that you have filled out. Now my question is, what do you do with the h up and h down? Like, do you average it? Do you do some more?
You concatenate it.
Okay.
Concatenate together to get like.
Yes, but now I am now doing all the other jugglery to go up. With I will still work with these two values, or I will.
Yeah, you'll work with this
new. Okay.
New value. You work with this new.
So there is no averaging or no kind of other things that you are doing.
No averaging. It just basically goes one forward, goes one backward, and concatenate, and your hidden state ends up being like maybe twice as big. Okay. That's it. That's what we do.
For why it's useful, here's this linguistic intuition example that linguists like. There are these garden path questions, which you can say the horse passed the barn, fell. So until I say fell, you have a totally different interpretation of the sentence. So sometimes it matters. So what has stated earlier sort of depend on what will be stated later on. Yeah.
Yes. Maybe I have an example on that. If you speak French, so this is everything put together. Again, there's nothing new here other than we have this new structure for the encoder, and everything else is essentially the same with what we've seen. So that model becomes our encoder. Okay, and note that finally, just notice like if we fix CI into this value, then we get our regular RN encoder and decoder. So we just fix it to this, and CI no longer depends on anything. So the experiments they ran, it essentially ran into, like with a whole bunch of English to French translation. Basically, they were trying to minimize. This makes no sense. I think it was trying to minimize the cross entropy between the target and the predicted. Because otherwise, this makes no sense to me. But anyway, the model size is 1,000. You stochastic gradient descent with this added delta. I think probably at that time it was state of the art, or maybe there's some other reason they choose this. Batch size is 80, and finally evaluated on blue score over the results that it got from beam search. And here is the reason why you do not see a lot of like abolition studies or like, because each model trains 5 days, and they probably have a deadline to meet or something.
What year was this?
2015.
15?
Yeah, I have more details like.
Just saying that 80 sentences is. Oh, but that's just a mini batch. Sorry, no, I thought that's a sequence.
Mini batch.
Vertical.
Oh, you mean sentence length?
Yeah. So
they were using 30 and 50, 2 variations. Oh, we'll see. Actually, oh yeah, right here actually. So there are essentially basic arguments that as the length of a sentence goes long, if you use this attention mechanism, they should perform better. So what they saw is
guys, if you want, and this is the open discussion, you can just ask, you can stop.
Yeah. So the question was, what if you go back to the previous one? What is the word embedding? No, just the one before. Yeah.
The one before?
No, the one you were on.
It's fine. What's the word embedding dimension 620 and means?
The word embedding?
Not here. It was in
Next
the
slide.
slide we were just discussing.
Next one.
Yeah.
Word embedding. So when you have inputs,
This okay.
yeah, you want to take a shot at it. Go ahead. You're
Word
just better
embedding
at
dimension. Okay, so there's a lot of details I ignore. So this comes from the not this paper, but what they actually doing is basically the Y, the output, is not a one-hot encoding. It's not like the vocab size. There's intermediary like embedding, which is set as 620, and then they use that maybe to do some further transformation into one-hot. So there's an intermediate like embedding representation, which was like totally shuttled all the way down to the appendix.
Same with your inputs, so X's and Y's. So for your X's, you look at the word, and then you project it to some embedding space, usually pre-trained, word to vec, or randomly initialized. And then that's dense representation, and then from there you go and start your. So basically, each item in your vocabulary is a unique embedding.
In some other like space where people have values for those words.
Yes. So if you're familiar with word to vec or PCAs, yes.
So now, and the same thing is done at the final stage of the when you are trying to encode it back. You also use that to find what it means. What's the more French equivalent word for that number?
Correct. So as Chen mentioned, when you your outputs would be embeddings as well, and you use beam search to select the most likely outputs, and you just pick the most likely as your. There are a few ways to do this as well. Also, just a quick note: the fact that it took there are a lot of methods these days, like binning, for example, that can make this much faster than it is.
You mean for the RNN model?
Because you mentioned it took like a few days.
5 days.
Yeah, 5
Oh,
days.
I have more data like you.
Yeah, like recently.
Sorry, we'll see that.
Yeah. Just want to say that there are like there are tweaks tricks that you can do to make it train faster than this. But
Sorry.
no, I just wanted to say you were saying something, and then we asked 2 questions at the same time.
I
Do you
don't
remember that?
remember. but just to follow up on embedding, I think, correct me if I'm wrong, it also helps with unknown tokens, because it probably has some kind of smoothing effect on the unknown tokens.
So you can still generate. So it doesn't directly address the unknown token problem. For that, there are methods that you can use, pointer generator network, for example. But it implicitly, the network knows that it's a different concept I'm talking about. It just cannot produce it because it doesn't have that vocabulary, that vocabulary item. But there are ways to make that possible. But your intuition is 100% correct.
Okay.
So what's beam size?
The what?
Beam size?
Where is leap size?
12.
Beam size. So beam size is when you get a bunch of probability of words. So at the end you use the beam search. Beam size. I don't have a slide for that. Yeah, if you can.
Sure. So like in beam search, basically your search space is exponential because it's a sequence, and for each one you have to look at the entire vocab to see which one is more probable. That's your basic search. So for each item you want to generate, you have to search your entire vocabulary. That's exponential, right? To reduce that, what you do at each time step, the decoding time, you keep only 3, say if the beam size is 3. If it's 12, you keep 12, and that's also another factor that it's a little bit costly. So you have to keep 12 items that are most likely.
What the opposite of beam search is probably searching it very greedily, because you can't do this whole exponential search. Maybe you just truncate it to the top 5, and step 1. At step 2, you also do the top probability, but it's not optimal because it's greedy. Can I say?
It is greedy. Yeah. So instead
no, I mean, beam search is like the opposite, a little bit opposite to that.
To some extent. So you're not only keeping 1. If you keep only 1, it's greedy. So if you're generating a sequence, you keep the most probable item. So you look at the vocabulary. You want to generate something. You pick. So because you generate an embedding at the end, right? At your Y is an embedding, right? Then you look at the entire vocabulary to see which one is most probable. We keep that, right? And if you only keep that and only add 1 item to it,
That's great.
then that's greedy, right? You can keep a few, so beam search is just a little bit better. You can keep like 3 most probable words. When you want to add the next item, you're not searching through all different permutations of your vocab, which is I think 2 to V. 2 is like your base, 2 vocabulary size, right? That's your all your permutations. You're not doing that. You're just doing 1, 2, 3 words that you have kept, or 12 over here, beam size, the most probable ones, and then for each of them, you're looking at all the vocab and compute the probabilities. So 3 times vocab size.
That's why you're talking about n-grams, I see.
Yes.
Okay.
Yeah. So your search reduces to 3 times vocab size. Okay. So 12 times vocab size, as opposed to 3 to B.
So another, they tried to do incorporate known and unknown. There's like separate like metric studies on that, and they compare that against first is a RN encoder baseline, encoder-decoder baseline, and second, this was the state of art. I think that it no longer is. This is basically again, correct me if I'm wrong. They're using like a massive vocabulary of kind of phrase matching in a way to do translation. So they still didn't manage to completely beat the system, but their point is, hey, look, we have an end-to-end neural model that performs very closely to the state of art. So here's the result. This is Moses is the state of the art. Again, they didn't manage to. In one particular instance, if they train it for a very long time, this star means like they trained for as long as possible until it didn't improve. And they somehow, on one particular test, where they just strip out all the unknowns and they kind of slightly beat Moses. But in other instances, they're still kind of below Moses. So
So Moses is this god of a baseline in machine translation.
So RN. Okay, I have it in the next slide. This is exactly the same table with the previous one. RN encoder baseline, what their architecture, they call it RN search. So again, it beats their baseline, in this case by a wide margin. And 30 means maximum length of sentence they accept. They discard everything that's longer than that. 30 and they do 2 variations, 30 and 50. So here is some comparison here. RN search 50 performs very well. RN search 30, for some reason, performance drops. Probably they haven't trained long enough. Probably I'm not sure what the reason is. But I think what they're emphasizing is the fact that this line doesn't drop.
Well, 30 is the number of tokens it's keeping, right? So it doesn't.
Right. So it should only be responsible for everything up to 30. So it still performs much better.
Yeah.
Okay.
Yeah.
So
Sorry, I didn't understand what the reason was. Can you repeat the reason?
why this line?
Yeah.
Because as the length of the sentence goes longer, this is actually also the discussion point. Like if you use like only RNN, it probably tends to forget if like it has seen previously. Because because the length of the sentence is too long if you use RNN. So maybe it is probably good at things that's close to the end, but not very good at things to the beginning. That could be one iteration.
Is the source problem that the information has to do too many hops to get?
Yes. That's the discussion point.
It's kind of like vanishing really in that
Yeah, I was more thinking along the lines that it can it even generate? So if you train it, I think it can. If you train it a sequence to sequence on only 30 words, and then expect it to generate 50, it can, yes. So I think, yeah. So it can generate 50 because you can just change your output sequence size. The thing is that there are different ways of making it stop generating.
Yeah, there's a stop token, for example.
You can have a stop token. You can milk your beam search, but I think your point stands true, regardless.
Yeah, it's a vanishing grid.
Yes, if you train it on 30 words, then it's trying to keep that much information in that way.
Okay.
Hold on, I'm still confused about this. So what is the horizontal axis here?
The blue score.
The blue score.
How well it performs.
No, that's
The metric.
Oh, horizontal. Sorry, how the length
Oh,
of
length of sentence.
How many tokens?
How many words in
If it's words, it could be
So
characters.
then what is 30 and 50 in the RNN search, 50 in RNN search 30? That's the window?
That's the max sentence length that they trained it on, I think.
These are the number of hidden layers,
Yeah.
like number of
No,
concepts.
no, I think it's a max.
50 is the anything that's during the training, anything that's greater than length 50 they discard. I think that's what they do.
So it either hasn't seen any sentences that are larger than 50 or they crop them. I don't know.
But
Maybe
then
it's
the
probably.
line goes beyond 50, right?
But they're training it
Probably
on-
weird. Okay.
Well, you
I
may have-
don't remember.
You probably do. You may have sentences that are larger. So at test time, you may have.
Also, you didn't train them, but you validated.
So it can
on
still
them.
generate,
Yeah,
as
yeah.
long as it generates. So
I
one way
see.
to stop it is use the stop token,
Sure.
and as long as stop token hasn't come by, it can still try to generate longer sequences.
But yeah.
So would the trend of the RNN search 50 be the same as the 31 if you went longer? Like
Right,
longer
that's what I'm
trends?
wondering. Yeah.
Like would it drop? down?
Our search-
Well, that's actually
that's
the
because of attention. You can see.
No,
No,
the
I
other
mean,
one's
yeah.
attention, but it's 30. So I'm saying if you had a longer sentence, would it
Yeah.
go down?
So if the horizontal axis goes
Oh.
to 100,
Yeah.
would
Oh, it
the
doesn't.
solid one drop to?
You would have seen
Probably.
at some point, but it's interesting that
specific?
it's still better than
Yeah.
the 30 at 40, right?
Like the 31 started dropping before
doesn't
30.
have anything with the sentence lifespan generated. So the reason that we have time step size is that when we want to train RNN, we cannot have infinite length training. We have to cut it, so it unroll it and train it. So here, for example, you unroll it for 30, you train it. So it's kind of truncated training batch.
So you-
time.
Yeah. So if I have 60 sentence line, I break it into two trunks of 30 and 30, and I have my actual layer of 30
Yeah,
units.
and you can
I
have
push it.
power
Yeah.
and output
Okay.
until you have.
And then do the
Maybe.
blue score
Okay.
and drop. Okay, cool.
Maybe that's it. I need to look at
So 30 and 50 in the legend, the window size for training. So you have a sliding window sort of thing, or you break them down to.
Yeah, so you break it down to 30.
Yeah, so I think it's the number of tokens you let your encoder receive.
Okay.
So you remember we had time steps. You have 50. You're reading 50 time steps.
But
You're encoding.
can be any size because you wait for the stop size the stop token to get.
Yes, you can. They limit it different ways. You can generate. You can make it generate 30 tokens no matter what. But like the last 15 of them could be stop token.
Yeah. So here when you have to run your length, you wait for example.
I think they stop early
So-
instead of like doing the 50 every single time because they do have a technique where they sort the sentence into like shorter sentence first and longer sentence later.
Yeah, binning.
Uh,
Yeah. If you
it's called binning. Okay.
Yeah. If you do that, so basically you sort of cluster sentences that are shorter next to each other. You can by much improve the speed of training.
I'm actually wondering, is that some kind of a curriculum learning?
Yeah,
Is that
it
what-
is.
It is. Okay.
So what does then this thing means, which we saw in few slides up before, that 1,000 hidden variables. So now we are talking about 50 and 30. What is
This is the hidden unit, the size of the hidden unit in here.
It's the size of the H, not the
size
size
of
of
the
the
H.
every token corresponds to a hidden unit.
So your hidden variables are the parameters of the network that you're
Yes.
trying to learn. You had multiple matrices, multiple W's and V's and H's and S's, and they all add to the parameters. Each one of them has like around 10.
So when you mean hidden variable, is just the combination of all of them. It's not
all
just
the
the
parameters,
H.
correct? All the
Okay.
parameters usually.
Okay.
So question about like your comment. how is it related to curriculum learning?
I didn't include it here, but during training, they're not just randomly sample everything. They're basically like, I remember like take like certain number of sentences. There's a sorting process where they kind of train the shorter ones first, and then gradually increase. So that's why I was asking you this curriculum learning.
Yeah,
I didn't include in the slides.
It's a big, I think it's Benjio stuff, basically. He used all of the curriculum learning stuff, and assuming...
Obviously, okay.
Assuming sentence length correlates with difficulty, the curriculum learning is actually just giving it the examples that are easiest first. I mean, it's similar. I think the intuition is that you're doing what you would do for a child. You wouldn't give it Shakespeare right away and be like, "Go learn, you're fine." Right? You start with, I don't know, children's books or something, right?
Yeah, some sort of initialization.
Yeah.
But also you don't have to, like, if you give it so if you want to generate, and most of your sentences, for example, are like of length 5 and you have only one that's length 20, you're computing a lot of, so you have a lot of you're wasting a lot of computation, because each time you're generating a 20, only because of that one sentence, you're generating like 20 tokens.
Pragmatics, yeah.
Okay.
But 15 of them are stop tokens. When you push the 5 token.
Yes, but your network will go
you
wild.
do want to clarify two things. One is this 50 is the length of the sentence. Second, in terms of attention, if we're talking about like looking at all 50 words, indeed, a later paper actually said, okay, probably not. That's not necessary. So they have they test the global and local, and they found like if they just do a window, it performs more or less the same. So maybe that's a yeah.
There are other languages too. So in German, your second verb gets moved to the end.
Yes.
Right? So you would have your pronoun verb, and then you have a bunch of things in the middle, and then you have your second verb at the end. But a lot of times, if you do the small windowing, you might forget your initial verb by the time you get to that.
Yes.
Okay. I wish I included like a Japanese example, because French, they commented like French to English is pretty linear. Pretty much the same thing. Like, except maybe occasionally here's how they also demonstrated why attention is important. European Economic Area in French is totally the reverse. So in here it's kind of like the dynamic matrix kind of fit. And in here, this is something, if somebody speaks French, please, this is what the example they gave me to demonstrate like soft attention as opposed to hard attention, which I don't fully get because I don't quite get there.
I think it's because that's a contract. It's basically saying a contraction, right? It would be le would be la, or la, and it would be le for on.
Yeah, they mentioned something like that. Okay.
Yeah, so that should be the man, but it's contraction. So it's just L apostrophe. So it's a soft attention because it's preserving some of the activation. It is the gender, but it's also the. So it's a gendered the. So
that's why you pay attention to man as well.
It's smeared now, and it's saying yes. It's both the identification. Yeah. Exactly.
So these two actually you won't know unless you look at both.
That's right.
That's basically
that would be something different, I assume, if that was a woman.
Okay.
Yeah. Well,
so that's their argument. That if you use hard attention, this probably could be wrong.
Correct.
The woman it would be last time, I think.
Yeah.
So you should probably wrap up in 5 minutes.
5 minutes. Okay. I don't have much else actually. So there's another sentence. This is the example they give. Again, so what they're saying is essentially this is wrong, but their model can correctly basically deal with long sentence. If that makes sense.
Yeah.
So here is some learning statistics, which is basically a number of, parameter updates, how many epochs they run, and this amounts to how many days? 5 days, and this is the GPU they're using.
5 days on a type.
And now it's the average condition probability sentence. Oh yeah, this is probably some performance metric. Like training, I guess is a log probability, and here's the depth set probability. this star is basically trained for as long as possible, 10 days, until things don't improve. Probably because their time is very limited, because every time these things are only 5 days. So some related work, I think I'm going to skip. This is basically some visual attention, papers on visual attention before. And this paper, I think, is worth looking at along with attention. This is kind of like a basic in-depth analysis, the things they kind of missed. And this guy Wang, he basically did more further study, and also the different alignment function he also came up with. His conclusion is that something like bi-directional may not be necessary, and maybe you don't have to do this global attention. Maybe local would also work just as well, along with some other conclusions. So summary, we have probably talked about. We talked about most of the points, and later works still okay. And here's the discussion question. So I think we talked about the. I guess my question is like, there's no kind of application study, so we don't know how much of improvement comes from what. Later, they did something to somehow do more analysis. This we talked about the effect of other energy function, and finally, if you really think about it, is this really a probability? It's not a probability. It's a magnitude. So why do you do softmax?
To make it probably?
Yeah. Maybe have some kind of. Okay.
I know, I evaded it.
Okay, I raised this point because I saw some paper that published just recently, like a few years ago. I forgot if it's sequence to sequence, but they did actually use LSTM with attention, and they did find that if you don't softmax it, it performs slightly better. The reason is being like softmax actually kind of changed the shape of the I guess the focus on each of those beams. So it actually tends to award a winner even more. I guess it has kind of suppress the runner-up in a way. But in a lot of cases, if the second to the best is important, then maybe not applying softmax is
or applying something else.
Yeah, so I guess it's a very interesting point. Is that maybe we just blindly sometimes okay,
Does
softmax.
it really have to be probably? I think it's also a normalization factor because your values don't really linearly grow.
Yeah. I think that's probably the main reason that they do it just to be safe.
Yeah.
But what happens? Would it be still okay or? So I think that's just an interesting point.
It is. Yeah.
So on Monday, Joseph will be presenting this. I think attention is all you need, which is my understanding is it throws in a lot of tricks. And also, I think what was the most good thing is the best thing is it got rid of RNN altogether, so that it trains a lot faster. So there's a lot of exciting things in this paper as well. I think this is the eye-catching title, but I think it's kind of justifies it.
Gets that attention.
Yeah, actually the paper is actually about. It's fitting actually in my understanding. Okay, so on Monday, not in here but in somewhere else.
Yeah.
Okay, that's all.